In this video, we're going to derive the pullback or vector Jacobian product rule for matrix vector multiplication. A matrix vector multiplication can be viewed of as a function that takes as an argument a matrix A as well as a vector x and then performs the matrix vector multiplication A times x, and let's call the result of that computation set, a vector set. Let's assign some dimensions to the quantities here. So let's say A is a matrix of shape m by n, so m rows, n columns. Then, by the definition of a matrix vector multiplication, x has to be an n-dimensional vector, and then set will have the row dimension of A, so set will be an m-dimensional vector. Of course, what we're going to derive will equally be valid for square matrices, so where A is a matrix from n by n, and the vector x as well as the vector set will be n-dimensional, but let's keep it as a rectangular matrix for generality. The task of the pullback or vJp rule is to backpropagate or pull back cotangent information on the output to the input. So let's call this backpropagate cotangent information on the output, which can be given as a set bar, which will be an m-dimensional vector, to the inputs of the function, so to A bar, which will be an m by n-dimensional matrix, as well as to x bar, so end x bar, which will be an n-dimensional vector. And by the way, this rule we're going to derive is also commonly seen within classical multi-layer perceptron feed-forward neural networks, as those usually consist of multiple layers in which we have an matrix vector multiplication plus some addition, so it's essentially an affine transformation plus some nonlinearity. Okay, how can we do that? Let's write down the general rule for a pullback. So the pullback on matrix A is given as the cotangent on the output transpose multiplied with the Jacobian of the function when derived with respect to A. So we derive the Jacobian of the function with respect to A input, and then we get the cotangent of A input by left multiplying this Jacobian with the cotangent on the output. And here I just introduced this transpose to indicate this left multiplication. A similar concept holds true for the backpropagation to x, which will be set bar transpose and then the derivative of f with respect to x. So we will contract on the numerator and here as well, and then we will get as a result the cotangent on the particular input to the function. However, here this is a little bit ambiguous since we're working in tensorial quantities, and in particular here, where we will derive a vector with respect to a matrix, we would get a rank-free tensor, so it is actually reasonable to work in index notation. So let us change to index notation. And for this, I first want to write down the primal computation index notation, or in other words, the original matrix vector product. And this one can be seen that set I is given as the function applied to A and x. And then we will here have Aij times xj. And this implicitly assumes the Einstein summation convention, in which if there is an index appearing twice in a product, we will sum over it. And this is essentially the definition of a matrix vector product. So we will get the ith entry of the output by contracting over the j's here in this Einstein summation convention. And as a consequence, we can then write down these two pullbacks. So we will first get AKL bar. So the cotangent on the input matrix A, index KL, is given as set I bar multiplied with d set I with respect to AKL. And here I didn't use the f anymore, so I just want to be like a little bit more concrete in that this is the derivative of the ith output with respect to AKL. And here we again see we have the contraction in the numerator. So we will have the cotangent on set and multiply this with set I, and then we have the dimension or the index KL also as the index that we have on the cotangent on matrix A. Similarly, we will get the cotangent xk as set I multiplied with d set I with respect to xk, and also a contraction here. And in order to find these expressions, we have to evaluate this derivative or this Jacobian. And I want to start with this quantity since it's a little bit easier. So let's say we will do that first and then afterwards this one. Okay, let's get started. Let's have this one first, and let me first evaluate this derivative. So let's evaluate the output of Zi with respect to xk. And for this, let us look at the primal computation in index notation. So if we derive Zi with respect to xk, we will first see that aij does not depend on x, so our derivative just propagates or applies to the xj. So we will get aij and then multiplied with xj with respect to xk, and we are deriving a quantity xj with respect to xk. You can think of it like deriving the jth entry of the vector with respect to the kth entry of the vector, and since this is the identically same vector, we will get a 0 if j and k are not identical, and 1 if those are identical. And this can be expressed in terms of the Kronecker delta, which is delta jk in our case here. So this will just be 1 if the indices are identical and 0 if not. So this is the derivative we get here. And if we then apply this in our pullback rule, we will see that xk bar is essentially set I bar multiplied with aij and then multiplied with the Kronecker delta jk. Then we can make usage of the properties of the Kronecker delta. Since it is 0 in some combinations of the indices and 1, it actually induces an index change. So effectively we could either change all indices from j to k, or we could change all indices from k to j. And here it makes sense to change from j to k because our output is in terms of k. So what we will get is we have an xk is equal to a Zi bar times xik. So the kth entry of the cotangent of the x input is given as a multiplication of Zi bar with aik. And here we see this essentially is a left multiplication. So we can move that back to symbolic notation. So back to symbolic notation. And then we see that xk bar is nothing else than, well, Zi multiplied from the left. So we could also equally represent that as a transpose multiplied with Z bar. And of course, then we wouldn't have the index here anymore. So we see that the cotangent on the input x is given as the primal on A transpose multiplied with the cotangent on the output. Okay, so far so good. That was number 1. Let's go to 2. So for 2, again, let us first evaluate the derivative. So the derivative of Zi with respect to akl. So let's look at the primal, and we see xj does not depend on A. So we will just have the derivative on A. So dAij with respect to akl multiplied with xj. Well, here, similar idea, just applied to matrices. And I mean, this generalizes to any kind of tensor ranks. Here we see that we will get a 1 only if the indices match identically and a 0 otherwise. And we can represent this as 2 Kronecker deltas by having delta ik and delta jl multiplied with xj. And then in total, we get that the cotangent on A index KL is given as Zi bar multiplied with delta ik, delta jl, xj. And here again, we will change indices, and let us change the indices such that we have the indices of the left-hand side. So we will get that A bar KL is equal to, here we change to K, so Zi K multiplied, or Zi bar K multiplied with XL. And essentially what that is, what we have here in symbolic notation, is an outer product. So we are multiplying the vectors such that they blow up into a matrix. So we could write in symbolic notation the following. So symbolic notation, we will see that the matrix cotangent is given as the cotangent on Z multiplied with the original primal on X transpose. So this is an outer product. And by this, we now completed the pullback rule on A bar. So in total, we can write the pullback rule for our matrix vector multiplication given the function. So this shall represent matrix vector multiplication. And then we have the primal input A, the primal input X, as well as the cotangent output Z. And then we have first our primal computation, which will be A by X, straightforward. And then we have two cotangent computations. We will first have the cotangent on A, where we will use that rule, which is Z bar times X primal transpose. And then the backpropagation on X will just be A transpose times Z bar. Then we can close that down and we see that is the original output Z. This one will be the cotangent on A, and this one will be the cotangent on X. And by this we have found the rule in order to backpropagate information or cotangent information or derivative information from the output to the input. A big thanks to all the patrons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you will find the link to the Patreon page down in the video description. I hope you enjoyed that video. If you did, then please leave a like and consider subscribing to the channel. There is more content on pullback and push forward rules or automatic differentiation in general. Here you will now see similar videos, and I hope to see you in one of the next videos.